Good day, everyone. I'm Jeremy Kumiya from Mapua University, and today I will present my study entitled Predictive Sensorless Tuning Method for Motorized Airflow Systems using Quadratic Curve Fitting. This study focuses on improving airflow tuning in motorized systems by using a predictive and sensorless approach. Instead of relying on a manual adjustment or continuous external airflow sensors, this method uses electrical power input and quadratic curve fitting to estimate and control airflow more efficiently. Airflow tuning is important in systems such as fans, blowers, and ventilation units because these systems need to maintain specific airflow levels during operation. However, in many production environments, airflow tuning is still done manually. This makes the process time-consuming, inconsistent, and affected by hardware variations between units. Existing methods may use trial and error, real-time sensors, or complex control logic. While these methods can work, they may increase cost, calibration time, and computational complexity. Because of this, the research problem is the lack of a standard sensorless and lightweight method for predicting airflow. This study addresses that gap using quadratic regression. The main objective of this study is to develop a predictive sensorless tuning method for motorized airflow systems using quadratic curve fitting. Specifically, this study aims to develop a quadratic regression model that can estimate airflow from electrical power input. It also aims to implement and validate the model using embedded Foxconn fan with real-time data. Lastly, the study compares the proposed curve fitting method with the conventional tuning method across low, medium, and high flow modes. The goal is to show that airflow can be predicted accurately without depending on external airflow sensors during final operation. The scope of this study is limited to sensorless airflow prediction using electrical power input and quadratic regression model. The experiment was conducted using one embedded Foxconn fan model, and it covered three operating modes: low, medium, and high flow. The system uses an open loop configuration. This means that during final predictive tuning, there is no continuous real-time airflow feedback. For the limitations, this study only focuses on quadratic regression, does not include full multi-fan validation, and external factors such as a long-term motor degradation, acoustic behavior, and environmental disturbances were not included. The system design is structured into three main layers: the hardware, firmware, and software. The hardware layer includes the ESP32 microcontroller, Foxconn fan, current and voltage sensing, differential pressure sensing, power drivers, and protection circuits. The firmware layer is managed by FreeRTOS or real-time operating system. It handles real-time tasks such as sensor polling, PWM control or pulse width modulation motor control, communication, and system coordination. The software layer was developed in LabVIEW. It provides a graphical user interface for monitoring data logging, curve fitting computations, and validation routines. Together, these three layers allow real-time data acquisition, airflow measurement, and predictive tuning across the testbed. This slide, we're looking at the airflow measurement setup, which uses custom Venturi tube. This tube is designed to measure airflow from Foxconn fan. We use the MPX V7002DP differential pressure sensor to capture the pressure difference across the tube. Here's how it works. As the air flows through the tube, it passes through the narrow section or the throat, which creates pressure difference. According to Bernoulli's principle, we can convert this pressure difference into a measurement of airflow rate. Think of it like a water pipe, where narrowing the pipe creates more pressure, and we can measure that to understand the flow. To ensure accurate measurements, I've optimized the tube's design. The inlet and outlet diameters match the fan's dimension, and the throat diameter is set to 57 mm. I also incorporated an extended diffuser with a gentle 4.9 degrees angle, which helps recover pressure and reduces turbulence. This is especially important when measuring low airflow rates. This slide represents the wiring diagram, the actual embedded testbed, and the test software interface. The wiring diagram shows the ESP32 is connected to the fan, sensors, power supply, relay module, OLED display, and communication interface. The actual test bed includes the fan, control box, power supply, sensors, and the LabVIEW software running on the computer. The purpose of this setup is to collect reliable power and airflow data during characterization and validation. The LabVIEW interface allows the user to monitor voltage, current, differential pressure, and flow rate while controlling the fan modes and recording the data. Before performing the airflow test, calibration was done to ensure reliable measurements. Ambient pressure and temperature were monitored using the BMP280 sensor. The recorded ambient pressure was about 998.34 hectopascals, and temperature was about 32.06 degrees Celsius. The ENA219 current sensor was also validated against a calibrated multimeter. The comparison showed that voltage and current readings were very close between the embedded sensor and the reference instrument. This calibration process is important because the predictive model depends on accurate power measurement and stable airflow data. This slide shows the motor power mapping. This is essential because it helps us understand the nonlinear relationship between the motor's electrical power input and the airflow rate. This means that we can directly predict airflow just from the power input without modeling the complex behavior of the motor. During characterization phase, the system sampled airflow every 100 milliseconds, while the PWM duty cycle was varied from 0 to 100%. Each step was allowed to stabilize for 5 seconds to ensure reliable measurements. I tested several models to best map this relationship, including linear, exponential, quadratic, and cubic models. The quadratic model was selected because it struck the best balance between accuracy and simplicity. With R squared of 0.9965, it accurately predicts airflow with minimal computational complexity, which is ideal for embedded systems. What sets motor power mapping apart from the curve fitting done later in the study is that the mapping specifically described the power to airflow relationship based on empirical measurements across different PWM duty cycles. In contrast, curve fitting uses this map data of motor power and airflow rate to create a general predictive model that can be applied in real-time airflow tuning without requiring continuous measurement of external sensors. This slide presents the motor map equation that models the relationship between PWM duty cycle D and electrical power P in the fan system. P of D is equal to 0.6705 D squared minus 28.206 D plus 597.79. This equation is crucial because it helps us predict the required electrical power for any given PWM duty cycle, which directly controls the fan's airflow. By using this mapping, we can estimate the fan's power consumption without needing additional sensor, which is the key to the sensorless predictive tuning method. While I did explore using cubic model, which showed a slightly better R-squared value but will require complex calculations and dataset, the quadratic model was prepared for its balance between accuracy and computational efficiency. In addition, I've identified a no-go zone for duty cycles below 40%. This range, the fan behavior was unstable, leading to poor repeatability of the airflow. This instability made the system unpredictable and not suitable for reliable operation. As a result, we decided to start tuning at duty cycle around 50%. At this point, the fan operates in a more stable region, where the system's performance is more consistent and predictable. This choice ensured that we get accurate airflow control without unpredictable variation. The slide explains the tolerance used for validating the airflow prediction. The system analyzed flow rate variability at low, medium, and high flow modes, using 50 samples of each mode. The highest standard deviation was 0.473 CFM at medium flow. Using a 3 sigma margin, the tolerance was set to approximately plus minus 1.5 CFM. This tolerance was used as a pass or fail band of validation. The target flow rates were 16 CFM for low flow, 20 CFM for medium flow, and 30 CFM for high flow. The design constraints include the use of only 3 fixed flow points, open loop prediction, hardware and firmware limitations, and the fact that the validation was performed only on Foxconn fan. This slide shows the curve fitting process flow used to model the relationship between power and flow rate. The process starts by reading the configuration file and setting the default power values. The system runs each flow mode low, medium, and high, and checks whether the measurements are stable. Once flow is stable, power values are collected for each flow mode. The system performs the curve fitting. This step involves using three data points, one for each flow mode, low, medium, and high. These points are used to derive a unique quadratic equation for the fan. The equation is of the form P of Q is equal to AQ squared plus BQ plus C, where P is the power and Q is the airflow rate. These equations allows us to predict the required power for any given flow rate based on the three empirical data points. The reason we use quadratic regression is that the relationship between power and airflow is nonlinear, meaning it's more accurate than linear methods. Quadratic model is embedded friendly, computational efficient, and fast enough for real-time use, which makes it scalable for production calibration in embedded systems. The slide presents the validation results of the curve fitting method. Across the 10 trials, all curve fitting tests passed. The low flow mean was 15.44 CFM, the medium mean was 21.9 CFM, and the high flow mean was 30.47 CFM. The residual equation is residual is equal to actual value minus predicted value. For flow rate residuals, low flow had negative 0.56 CFM, medium flow had negative zero point 0.1 CFM, and high flow had positive 0.47 CFM. All of these values were within the plus minus 1.5 CFM tolerance band. This confirms that the curve fitting method produces repeatable and reliable airflow prediction across all three operating modes. This slide presents the conventional tuning method used as the benchmark. Unlike curve fitting, conventional tuning relies on repeated power adjustment and trial and error. The system starts from a default power value, checks the measured flow rate, and then increases or decreases power until the airflow reaches the acceptable range. This process works, but it takes longer because it depends on iterative adjustments. In the table, some conventional tuning trials passed, while others failed, especially at high flow. This shows that the conventional method is more sensitive to overshoot, variability, and longer tuning cycles. This slide compares the curve fitting method and the conventional method. In terms of flow rate accuracy, the curve fitted model produced lower and more stable residuals. In terms of power efficiency, the curve fitting method achieved the target flow rates using less power than the conventional method. In terms of tuning time, curve fitting completed the process in a single predictive pass and reduced tuning time by more than 86%. For repeatability, curve-fitted method had the lower standard deviation in both flow rate and power. Overall, this confirms that the curve fitting is more accurate, faster, and more consistent than conventional tuning. In conclusion, this study successfully developed and validated a sensorless predictive tuning method for motorized airflow systems using quadratic curve fitting. The method achieved reliable airflow prediction without using external airflow sensors during final tuning. The quadratic power map achieved an R-squared value greater than 0.996, showing strong model accuracy. Compared with conventional tuning, the proposed method reduced calibration time by 86% and improved power efficiency by around 20 to 28%. The main contribution of this study is a lightweight sensorless and production-ready framework for automated airflow calibration. For future work, the method can be extended to multiple fan models, dynamic voltage and load compensation, and long-term diagnostic monitoring. That concludes my presentation. Thank you for your time and attention. This study demonstrates that sensorless predictive tuning can optimize airflow systems with improved efficiency and significantly reduce calibration time. I'd be happy to answer any question or discuss the potential applications of this technology in various industries.